Hello, welcome to the first lesson into our fourth unit of this series looking into states of matter. Our lesson today is called the gaseous state and the ideal gas law. Our lesson objective is to understand how to calculate and manipulate the ideal gas law equation and explain its limitations. As always, the outcomes from the curriculum we'll be addressing just below there. So states of matter. I'm sure we're all familiar with different kinds of states of matter. We've got our solids, our liquids, our gases. When we are considering why a certain substance is going to be in which particular state of matter, we consider the particles to be acting like very small spheres essentially. It's a sort of particle theory idea behind the states of matter, that there's just these small spherical objects that are in constant motion, and then depending on their chemical properties, depending on the structure and bonding, will dictate what state it's going to be in at any given temperature or pressure. So we consider all matter consisting of very small particles that are in a continual state of motion. States that matter will exist in depends on how these particles are interacting with each other. This will depend on their bonding and structure. Now, I've just finished a whole series on the different types of chemical bonding, so this states of matter leads on very nicely from that video series that we just finished. So we've got our types of bonding. We've got our metallic, our ionic, and our covalent. And then within our covalent, we've got our intermolecular forces, our dipole-dipole, hydrogen, and our van der Waals. So depending on how strong or how weak these bonding and these interactions are between certain particles will determine what type of state it will be in at, let's say, just at room temperature. And it also depends on the structure. So we've got 5 kinds of structures. We've got simple atomic. This is where we have just an atom, such as noble gases, just a helium atom, a neon atom. They're going to have weak van der Waals forces, weak forces of attractions, simple atomic structure. Simple molecular, similar to the simple atomic, only with molecules. And then we've got our 3 types of intermolecular forces. So depending on how strong they are, whether it's dipole-dipole, whether it's hydrogen or van der Waals, will determine the state it will be in. Giant ionic and giant metallica, we've done giant metallic rather. We've done a video series on both of those there. And then this giant molecular is something new that we're going to look at within this unit. So depending on the bonding and structure will depend on the state of matter that it will be. We have a gas where we have no fixed shape, no fixed volume. We have particles moving at very high energy, randomly colliding with one another. We have our liquids where it'll take the shape of the container it is in, moving less kinetic energy than in the gas. And then our solid where we have a fixed shape and a fixed volume where the particles will be vibrating around a single point. So this lesson is going to focus primarily on the gaseous state. Let's look at some properties of gases. So there's this theory called kinetic theory, this kinetic theory of how the particles are interacting with one another, that states the theory that particles in gases and liquids are in constant movement. The kinetic theory can be used to explain the effect of temperature and pressure on the volume of a gas as well as rates of chemical reactions. So it's this idea that we have our particles in the gases and in the liquids as well, constantly moving. Essentially kinetic energy is just the energy from movement. So kinetic theory, the theory that they're all moving. Makes a number of assumptions here. We assume that the particles are moving rapidly and randomly. Assuming that the volumes of particle is negligible. Assuming that there's no forces, whether attractive or repulsive, between the particles. No kinetic energy lost in collisions. And the gas temperature is related to the average kinetic energy of the particles. Now, most of these assumptions we know are false. For example, we know that even the weakest forces, even our van der Waals forces, will have some small amount of attraction or repulsion. We know that their particles are going to have a volume. So this makes the idea that this is ideal gas that doesn't really exist, but it follows all of these assumptions versus the real gas that we see in everyday life in the laboratory that won't follow these assumptions. However, we can still get theories and equations and gas laws from these assumptions that really do model very closely our real gases and make it very useful for certain experimental ideas. So the gases we encounter don't fit this exactly, however they come very close. Specifically, our noble gases like the neon and helium, these are small, these are very low intermolecular forces. So if we look at some of those assumptions that said the volume of particles is negligible, no forces, whether attractive or repulsive between it. Our ones like helium and neon, most closely, we'll model this. And then we've got the ideal gas model starts to fall apart at lower temps and higher pressures. We will look at why later in the lesson today. Righto, let's look at some concepts that we need to be familiar with. Pressure, volume, and temperature, all things that will dictate how a gas is acting. Firstly, pressure. Pressure is the force applied perpendicularly to the surface of a closed container. If I go over to my whiteboard and draw a container, let's have a look. I got container there, and then it's a closed container, so I have some sort of lid on it. And this lid's going to be able to move up and down for reasons that'll become apparent in just a second. So if I got a gas in there, let's say I've got 5 gas molecules. 1, 2, 3, 4, 5. These gas molecules are all moving and colliding and moving around randomly at different directions. So what the pressure is the force that is exerted when these gas particles hit the sides of the container. We get a perpendicular force, perpendicular meaning at a right angle. So they're all moving randomly, and every now and then they will hit the wall, and we'll get a force exerted from that collision on the container, and that is what the pressure is. And this guy can be going up like that. So pressure is the force applied perpendicularly to the surface of a closed container. Gas particles hit the wall of the container. So we can talk about a relationship between pressure and volume, because if you increase the pressure, that's going to be the same as decreasing the volume. Let's consider that. Let's say I've got a certain pressure here, P. That's the force that all the gas particles are colliding at the wall with. If I were to double the pressure, let's say 2P, that means that these particles would be hitting the container with twice the amount of force, so we get double the amount of pressure. If I was to half the volume, so I use my machine, this lid closes down a little bit, and I get a second container with the same amount of gas particles. I haven't changed the amount of gas particles in there, but what I have done is I've halved that. So we've now got, I'm no good at drawing lids today. So we've now got half the volume that we originally had. We've still got the same number of gas particles in there. I've still got 5 gas particles. 1, 2, 3, 4, 5. Now these will be hitting the cylinder, they'll be hitting the side of the container with that same original pressure. However, because the volume is now half the amount it was originally, we're going to be hitting those walls twice as frequently. If you just sort of consider that, if there's just half as much space, then they're going to hit twice as often. I think that makes sense. Hopefully that makes sense to you. So what we could say there is that decreasing the volume will be the same as increasing the pressure. So if we have what am I trying to say here? Increasing the pressure is the same as decreasing the volume. So 2P will have the same force exerted as half the volume. So if I got half the volume here, that would be the same as doubling the pressure over there. And what we call this is an inversely proportional relationship, inversely proportional. So that means that as you increase the pressure, that would be the same as decreasing the volume. As you increase the volume, that would be the same as decreasing the pressure. Inversely proportional. And you can graph this like so. If I draw an axis real quick, down here. Rightio. So I've got y-axis, and I've got an x-axis, like so. If I put volume on my y-axis, now it's inversely proportional. So that means that volume is directly proportional to 1 over the pressure. And that's what I put down the bottom here. I have 1 over P. So as we increase the volume, we decrease the pressure, and we have an inverse proportional. So volume is directly proportional to the inverse of 1 over P, like so. Therefore, volume is inversely proportional to pressure, like so. Excelente. What else do we have here? Same as volume being proportional to 1 over the pressure. Draw a graph to illustrate. Done all that. Okay, where does temperature fit into all of this? Increasing temperature increases the kinetic energy of the particles. And really, temperature is just a measure of the kinetic energy of the particles. So kinetic energy, kinetic means movement. It's the energy that particles will have when they're moving. If you increase the temperature, you're essentially just giving those particles more kinetic energy. You're just making them move faster. Increasing temp increases the kinetic energy. This will increase the force exerted on the container and thus increase the pressure and thus increase the volume. So you could look at them, two different things. Increasing the force will increase the pressure. Increasing the force could also increase the volume. Let's draw some diagrams to illustrate that. Let's say that I've now got this container and I'm going to erase this container. This has a certain temperature T. Now, if I were to increase the temperature, I would make these particles move faster. If this couldn't move, if this lid was fixed in place, that means that the particles would be hitting the walls of the container with more energy. Therefore, it would be exerting a greater pressure. So if you increase the temperature, you will increase the pressure. What about if this lid could move? If I was to increase the temperature, what that would do, I'll just very crudely draw my container over here, that would increase the volume because they would be colliding with this lid with more force. And let's say if the lid could lift up, it would increase the volume. So then I would have my same 5 gas particles with the increased temperature. If they were moving faster, they would increase the volume of the container because they would push the lid up and would get all that again, yada, yada, yada. So what this means is that our temperature is directly proportional to the volume. So volume is directly proportional to the temperature. So if I was over here, if I double the temperature, so if I go 2T there, I will double the volume 2V over there, like so. We call this a directly proportional relationship. As you increase the temperature, you will increase the volume. So unlike over here, we had an inversely proportional where it was doing the opposite. Over here, I'm going to draw a directly proportional relationship. Y-axis, x-axis. So I got volume here. Only on this side, I've got the temperature. So it's directly proportional. So as you increase the temperature, you will increase the volume like so. The volume is directly proportional to the temperature. Doubling the temperature will double the volume. Therefore, volume is directly proportional to the temperature. Draw a graph to illustrate we have done that just there. So why are we talking about all this? We can use all of these relationships and all the maths involved with these types of relationships and how you get graphs, how you get equations from graphs and stuff like that. We can combine all these relationships and all that maths to get the ideal gas law and the general gas equation. So the ideal gas law. An ideal gas is a gas whose volume varies exactly in proportion to the temperature and exactly in inverse proportion to the pressure. So the ideal gas is following these relationships exactly. So if you were to double the temperature, you'd double the volume in an ideal gas. If you were to double the volume, you'd half the pressure in an ideal gas. But remember, this has all those assumptions. This is assuming there's no intermolecular forces. This is assuming there's no volume. Volume is negligible. It's assuming all this stuff. So that's why we have the ideal gas, which doesn't exist, but we have real gases. But we can use this concept of an ideal gas and this general gas equation to very closely model how real gases behave. So we have this ideal gas law, and we can show that mathematically with what's called the general gas equation, which is this, another one of those ones that you're going to want to paint on the inside of your eyelids. It says PV is equal to nRT. Let me come over to the whiteboard and we'll write that down here. So mathematically, pressure times the volume is equal to the number of moles times by R, which is a constant that we'll talk about in just a second, times by the temperature. So we have a whole lot of variables and we have a number of units that these variables need to be in. I might mix my colors up with a little bit of blue. P is P for pressure. Pressure is measured in this equation in pascals. Now there's a number of units for pressure. There are kilopascals, there's atmospheres, there's millimeters of mercury. Now, this equation, there's a bunch of different ways you can sort of do it because all these variables can sort of have different units. So we're going to look at one specific variation of this where our units need to be very specifically what I'm writing on the board, and if they're not in this, you would need to convert into those units. So pascals would be this for pressure. Pascals is the unit of pressure. Our V stands for volume. Our volume is in the units of meters cubed in this specific case. So if they're not in meters cubed, you will need to convert. N, I'm sure you remember N. N is our number of moles, and that is in the units of mole. R, now R is a constant in this equation. If I go over the top here, won't be cut off. No. R is what's called the gas constant. And this is why the units are so important, because depending on what units you have will depend on the value for R. With the units we've got, we have a value of 8.31 joules per Kelvin per mole. 8.31 joules per Kelvin per mole. Now, essentially, all this gas constant is doing is just mathematically linking our energy to our temperature. So it's saying you need 8.31 joules, so joules is a unit of energy. You need that much energy for every temperature increase, for every mole increase. But we can just remember it as this value. And then finally, T. T is our temperature, but it's in this units called Kelvin. Now, you'll often see temperature in degrees Celsius or something like degrees Fahrenheit if you're in the North Americas. But Kelvin, Kelvin's a much less arbitrary unit of temperature. Because when we talk about degrees Celsius, it's pretty arbitrary. They've just decided that it's going to be based on water, right? So 0 degrees is when water freezes, 100 degrees is when water boils, and we'll just put increments in between that. Now, this is good for us in everyday life because most of our temperatures that we experience will fall somewhere within this range or something sort of tangible. So if we know minus 10 degrees, we know that's going to be cold. 45 degrees, we know that's going to be quite hot if we're talking about weather. What Kelvin's is a much less arbitrary and a much more scientific scale. So Kelvin says that 0, at 0 Kelvin, that is absolute 0. You can't get colder than 0. So 0 is where it's so cold that all particles stop moving. There's no movement at all. Because even in something like solids, it's a common misconception that the particles aren't moving in a solid. The particles are moving, they're just vibrating. But at this absolute 0, all the movement has ceased. The particles don't move at all. So it's based on that. And essentially, how you convert between Celsius and Kelvin is this absolute 0 Kelvin. So this point where there's so little energy, there's no energy that the particles can't even move, is at minus 273 degrees Celsius. So therefore, 0 degrees Celsius is simply going to be 273 Kelvin. One thing about Kelvin is you don't have a little degree sign, it's just K. There's no degrees K, just K. So if you want to convert between Celsius and Kelvin, you've just simply got to add 273. So if you had 10 degrees Celsius, that would be 283 Kelvin. So you've got to make sure your temperature's in Kelvin for your ideal gas law. Now, the useful thing about this is depending on what you're given, you can calculate a whole number of different things because you can rearrange for each variable. You could rearrange so that P is your variable, so you would get P is equal to nRT over V. You could have T is your variable. You can get T is equal to PV over NR. So any one of these you can make the subject of the equation. I'm not going to go through each iteration of how to rearrange equations. There'll be lots of other videos that you can quickly search up if you need a refresher of that. But let's do an example of how you might calculate something. Let's say, question, what is the volume of 0.5 moles of CO2 at a pressure of 150 kilopascals and a temperature of 19 degrees Celsius? If you want to have a go for yourself, this would be a good chance to pause, see if you can convert and plug all of those equations to get an answer for volume. If not, or if you've done that and you push and play, let's go through it now. How would I approach this? All right, where's my marker? First thing, we got to work out what we're calculating. So it's asking us what is the volume. So we've got to make volume as the subject of the equation. Rearranging that, volume is equal to nRT over P. Then as we do, I'm going to collate all my information and make sure they're in the correct units. We are given a number of moles of 0.500 mole. All good there, no dramas, N is in mole. We're given a pressure of 150 kilopascals. Bam, bam, we need our pressure to be in pascals, all right? So go between kilopascals and pascals, we got to times by 1,000, so we got 150,000 pascals. Again, I'm not really going to go through how to convert units, lots of other videos you can find. And we've also talked about it a bit earlier in the course, so I'm just assuming we know how to do that at this point. And our temperature is equal to 19 degrees Celsius. No good, we need it to be in Kelvin, so we've just got to add 273 to that, which will give us 292 K. Swell, and our R with all these units is going to be 8.31. That's a value that, I mean, usually it's just going to be given to you, but not too hard to remember that one, 8.31. Write it out 10 times if you need to know it. Alrighty then, so we plug all of these into our equation. 0 times by 8.31 times by 292 divided by P, which is 150,000. Let me grab my calc. If you punch all of these in, 0.5 times 8.31 times 292 divided by 150, 1, 2, 3, you will get an answer of 0.008 meters cubed. Our volume with these units has to be meters cubed. And if we go over here, we hopefully get that. We get 0.008 meters cubed. Significant figures and stuff, obviously always important, but for now we're just introducing the idea, so we won't worry too much about that. Let's keep going. We can take this one step further and we can work out the relative molecular masses of certain things, because in our gas equation we have this N variable. Now if you think back to some of the very first lessons we had, it's been a while since we pulled Old Faithful out to have a go on it, but we know that N is equal to M over M. N is equal to M over M. So we can essentially put this in there in order to get both M and relative molecular mass as variables that we can also play with. So if I put N is equal to M over MR in there, I would end up with MRT over MRP. So now we can rearrange to get both M, both the mass and the relative molecular mass, as subjects for our equation, which would look like this. So we know that PV equals nRT and that N is equal to M over MR. So if we put this N into the equation when it looks like this, we would get PV equals MRT over relative molecular mass. So therefore you could rearrange to work out the relative molecular mass given that. And this is really useful because experimentally, I mean, you can get the mass, you can get the temperature, you can get the pressure, you can get the volume. R is a constant, so you can work out the relative molecular mass of unknown compounds. For example, have a go at this one. If you're playing along at home, you can pause and have a play. Otherwise, we'll do it right now together. A 2.0 decimeter cube flask, I'm assuming that's meant to be flask, contained 5.80 grams of a gas. Calculate the relative molecular mass if the flask was Well, it was late at night when I was writing this. At 200 kilopascals and 20 degrees Celsius. All right, let's find out what the flash was. So when relative molecular mass is the subject of the equation, it looks like this. Mr is equal to mRT over PV. Rightio. So let's collate all the information we have. We have a volume of 2.0 decimeters cubed. Alarm bells, we need our volume to be in meters cubed. So we've got to divide this by 1,000, 0.002 meters cubed. Again, other videos you can look up if you need a refresher of how to convert units. We've also covered it earlier on in some earlier videos. We have a mass of 5.80 grams. No wuckers there, that's all good. What was it? The flash was at 200 kilopascals, so our pressure is equal to 200 kilopascals. No good. That's got to be in pascals. Times that by 1,000, 200,000 pascals. And 20 degrees Celsius, our T is equal to 20 degrees Celsius. No good. We need that in Kelvin, so we got a plus 273, so 293 Kelvin. And our value for R is equal to 8.31. Now, as you can see, before we've even looked at this equation, there are a number of steps we've got to do. So that's why it's really important that you are making it very clear what you are doing so that people who are marking can follow your work and give you mark where marks are due. So you really, every time you want to be collating your information, you want to be showing your conversions, you want to be showing the equation you're using. Don't just put a bunch of numbers on the paper because, I mean, your markers aren't going to want to have more work than they already have. So at this point, we can plug all these into our equation. Our mass was 5.80 grams. Our R, I won't put units in it, that'll just get confusing. 8.31, our T, 293, our P, 200,000, and our V was 0.002. Get old faithful, old mate calculator, plug all this in, 5.80 times 8.31 times 293, like that. And then we got to divide that by 200,000 multiplied by 0.002 should give us an answer of 35.305. Let's look at significant figures this time. Units, grams per mole minus 1. Remember, our answer is only as accurate as our least, or only as precise, maybe is the better word to use, as our least precise measurement. We were given 2 significant figures, 3 significant figures, 3 significant figures, 2 and 2. So we've got to have 2 significant figures, so it'd be 35 grams per mole to 2 significant figs. Lovely jubbly. Let's check the answer and hopefully it is the same. We get 35 grams per mole. All right, let's just finish up looking at these limitations that we briefly touched on earlier. To go back, the assumptions that we make for this ideal gas law and then subsequently for all this gas equation and calculations we make for that, we're assuming they move rapidly and randomly. We're assuming that molecules have a negligible volume. We are assuming that no forces are between the molecules, no kinetic energy is lost in collisions, and gas temperature is related to the average kinetic energy of the molecules. So fresh off your head, if you're coming in from the last unit, straight away you should be getting alarm bells about these no forces between the molecules. We know that. And then of course there is going to be some sort of volume on the molecules because they're taking up some sort of space. So we know that there is attraction and repulsion between the molecules because of our intermolecular forces that we've looked at, dipole, hydrogen and van der Waals, and we know the molecules will have volume. These differences are particularly noticeable at very high pressures and very low temperatures. So this is where this gas law particularly falls apart. At high pressures, the volume of a real gas is often considerably larger than the ideal gas. So we have this volume is negligible, is really falling apart at high pressures. And at very low temperatures, the pressure of real gas is often considerably less than the ideal gas. And at certain combinations of low temps and high pressures, the gas can undergo a phase change, where our ideal gas law isn't considering any sort of phase change. And with that, we conclude our first lesson on states of matter. What have we looked at? We stated the basic assumptions of the kinetic theory as applied to an ideal gas, explained qualitatively, so using words, in terms of intermolecular forces and molecular size, the conditions necessary for a gas to approach ideal behavior, the limitations of ideality at very high pressures and very low temperatures. And we've stated and used the general gas equation, PV equals nRT, in calculations, including the determination of relative molecular mass. Tasks, if you want to consolidate your understanding for this lesson, you can work through those one column at a time from the bottom working up. Great, thanks for joining me. From here, we now go into looking at the liquid state and the solid state in the next coming videos. So I will see you on those. Ciao.